And this forms a optical phonon mode, a transverse optic mode, which is shown here against temperature. And if this mode becomes soft and lowers it in frequency as you cool down, there's an opportunity for a structural phase transition. And in the ferroelectric case, if this mode frequency goes all the way to 0, then the position of this ion becomes unstable, and it shifts to a non-centrosymmetric position, as shown here. And then now we can see that there's more positive charge at the top of the unit cell and more negative charge at the bottom. And we have a case of spontaneous polarization. And this polarization can be switched by an applied electric field in the ferroelectric phase and results in hysteresis, as shown here. So you might be wondering, why am I talking about insulators in a strongly correlated electron systems conference? But it turns out that you can actually dope itinerant electrons into a lattice such as this in various different ways. And those electrons, in many cases, can feel very strong interactions. But before we get on to the metallic cases, I've got here some examples of ferroelectric quantum phase transitions in a diversity of different materials. So here we can see barium titanates that I was just speaking about. And with around 60 or 70 kilobars, you can tune this phase transition all the way to absolute 0, where it undergoes a quantum phase transition between two different ground states here. Here's another example in organic materials, tris sarcosine calcium chloride, where you can dope, in this case with chemical substitution. So doping bromine for chlorine suppresses the transition, and then around here at 0.7, there's a quantum critical point in this system. We also have the electronic or charge transfer type of ferroelectric, where in this case, in the paraelectric phase, there are no charged ions in the lattice, but at the transition, electrons move from one atom to another, thus creating ions and a ferroelectric state. So here, this is due to the motion of electrons rather than the motion of ions. And again, in this case, this work from Japan, you can tune with pressure to a quantum critical point down here. And then finally, we have a case of isotope tuning to reach a quantum critical point. So in the case of strontium titanate, you can change the oxygen-16 isotope for oxygen-18, so just adding 2 extra neutrons in the nucleus. And that's enough to push the system from being an incipient ferroelectric to being a long-range ordered ferroelectric with a transition at 25 Kelvin. And then by changing the percentage of oxygen-18, you can tune that down to a quantum critical point. And then finally, one more example is a ferroelectric relaxer, which is a bit like a electric dipole glass. And in this example of potassium lithium tantalate, you can actually use frequency and chemical substitution to drive the glass transition temperature precisely to absolute 0. So then this material can be made disorder-free, yes. This is new work which is just coming out soon. So at the moment, the role of disorder is not known in this case as yet, but it can be made. This particular work is on polycrystalline ceramics. Single crystals have not yet been prepared, but there are cases where you can then tune a dielectric electric dipole glass transition to absolute 0. We really don't know whether it's a self-generated one or whether it's due to oxygen vacancies or so in this case. So what's interesting about the quantum critical point is that there's a very large region here shaded in yellow, the quantum critical regime, which opens up when you suppress a transition to 0. And in this region of the phase diagram, you need both dynamics and spatial fluctuations of the order parameter field to understand the thermodynamic behavior. Whereas at a classical transition, it's just the spatial fluctuations of the order parameter that affect the thermodynamics. And the other interesting point is that close to the quantum phase transition, one often sees the emergence of new states of matter. And so it's interesting to ask what could happen in the case of the ferroelectric under those conditions. So what's different and interesting about ferroelectric quantum criticality? Well, it's a new quantum liquid to explore, in which quantum criticality is arising purely from the solid state lattice. It's not coming from electron charges or spin degrees of freedom. Quantum critical fluctuations have been observed up to 50 Kelvin or more, which is often quite higher than in electronic systems. Ferroelectrics have not only short-range interactions, but long-range dipole-dipole interactions. And usually coupling to the lattice strain is important. So that can lead to quite a rich quantum action and a rich phase diagram. So as I mentioned earlier, electrons can be doped or injected into incipient ferroelectrics and experience strong interactions. And then finally, since ferroelectrics couple to the electric fields, they can be tuned by voltage gates or strain, so they're often important for applications as well. So in order to understand the yellow region in ferroelectrics, I'm not going to go into detail of the theory today, but just to outline the kind of models which are used to do this. So here we have a free energy or action expanded in the order parameter, which is the polarization, up to fourth order. We have a time-dependent gradient here term and a spatial gradient term here. And we also have, as I mentioned, anisotropic long-range dipole interactions. And if we treat this using a self-consistent phonon model or self-consistent field model, which is analogous to the self-consistent renormalization model in itinerant electron systems, we can see that close to a classical phase transition, we recover the Curie-Weiss form, where the inverse electrical susceptibility varies linearly with temperature. But close to the quantum phase transition, quantum critical point, we have that the inverse dielectric susceptibility here varies as t squared, quadratically. And in the limit close to the quantum critical point, you can actually express it in a closed form analytical solution here, where these parameters here, delta and v, is the optical phonon gap and the speed of the phonons as the gap gets lower. And A and B, A naught and B naught here are the parameters from the equation of state. So these are determined from independent experiments at 0 temperature and are not fitting parameters in this theory. So we can test out this kind of, investigate these materials here experimentally. So we did measurements on a 45 millikelvin adiabatic demagnetization refrigerator, where you can do very nice, precise, smooth sweeps in temperature from low temperature up to room temperature. And this is fitted with miniature coaxial cables to measure the capacitance of the sample, which is proportional to the dielectric susceptibility. And also for later, we did measurements in a piston cylinder pressure cell. So here is the case of the isotope-tuned strontium titanate. And this particular curve here is measured very close to the quantum critical point at about 45% oxygen-18 substitution. And you can see here that the measured inverse susceptibility has this remarkable t-squared form. And this is the model calculation result here without any fitting parameters. So there's a very close agreement between theory and experiment without any fitting, coming from a simple quantum criticality model. So yeah, if you just put in these numbers here, it'll generate this curve in blue. So here is a more detailed phase diagram for strontium titanate, which has now been mapped out by Koch and co-workers in Cambridge. And we see here suppression of the ferroelectric transition, a large quantum critical regime here where you have a quadratic form of the inverse susceptibility, and also a divergence of the Gröneisen parameter, which we've measured here, which is very unusual in an insulator. And then below this line here, you have a deviation away from the t-squared because there's a gap in the transverse optic phonon spectrum in this part of the phase diagram. So here we have a quantum paraelectric, and in fact we have what we call a quantum polar acoustic, because here the strain is coupled to the polarization. So the fluctuations in the strain actually renormalize the ferroelectric susceptibility in this part of the phase diagram. And then at very low temperatures, we observe something quite strange, which is just suggestively titled as an instant on liquid, because here we see very slow modes which are behaving classically because they're so slow down here. And from measurements of thermal expansion, thermal conductivity, and piezoelectric resonating ultrasound spectroscopy, that it's possible that in this part of the phase diagram down here, in the paraelectric side, close to the quantum critical point, we could have some type of polarization textures, which are slow-moving modes. So this is, here I've shown the case in itinerant ferromagnetic systems where vortices and skyrmions can form close to the quantum phase transition. We believe that these could also form as polarization vortices close to a ferroelectric quantum phase transition. Sure.
So for MNSI, this comes because of the Shelinsky-Moria type.
Mm-hmm.
There's no such thing in your...
Sure, yeah. So there's actually many different ways of getting these kinds of skyrmions or vortices in materials. One of the ways that it can come from, as I mentioned earlier, is coupling to strain. So the strain field is highly anisotropic. And when you integrate out strain fluctuations and see what happens to the polarization, you can get these kinds of textures forming. But they can also actually show up purely from the phi to the 4 field model with no other fields. We can talk about that later. So now we want to introduce electrons into the lattice and see what happens to electrons. We use strontium titanate because it's well known that you can make this metallic. And one of the ways you can do that is just by heating it in a very high vacuum, very good vacuum at high temperatures, and then oxygen comes out of the lattice. And oxygen vacancies lead to additional electrons which form bands. Another way you can do it is using ionic liquid gating. So just pure strontium titanate and then electric field injection of carriers or perhaps electric field subtraction of oxygen atoms causes the sample to become metallic. And in both cases, the ionic liquid gated version and the bulk samples actually become superconducting at low temperatures. So strontium titanate was the first of the oxide superconductors discovered in the 1960s. This comes from Alex Muller's development of superconductivity research in oxides. And the superconducting transition temperature is less than 1 Kelvin, quite low. And then that led to a development of perovskite oxide research, ending up with a high temperature copper oxide superconductors. But in fact, superconductivity in strontium titanate has been not understood very much right up until the present day, in a similar way to the cuprates. Of course, there's been much less attention on strontium titanate. But here we show the superconducting transition temperature versus carrier density. And we have here a dome of superconductivity. And on the left-hand side, of course, we're reaching an insulating state. So it's clear to understand that Tc should drop down here as the Fermi surface collapses. And then at the high end, the question is, why does the superconducting transition temperature fall at higher carrier densities? And we'll see that that could be related to the screening of the interaction by the conduction electrons. These two red points are the superconducting transitions measured in the layer material, strontium titanate on LTO. So although Tc is very small, less than a Kelvin, the density of states is tiny. And how could it possibly be that something, even superconductivity is being measured below 10 to the 18 electrons per cubic centimeter? How could such a material be superconducting at all? Normally, you would think more like nano-Kelvin or micro-Kelvin, not 1 Kelvin. So that suggests that although Tc is small, the interaction pairing up the electrons is incredibly strong. And if you would scale up the density of states to normal metallic density of states, you would have a superconductor above room temperature. So it's worthwhile trying to understand what is the mechanism for superconductivity in this case. And there's been many proposals over the years, starting with multi-valley transition processes. But strontium titanate, in fact, doesn't have any multi-valleys. It has one Fermi surface pocket at the zone center, as shown here. So a multi-valley kind of model for superconductivity is not effective here. And then various other cases have been tested out, such as superconductivity arising from the acoustic phonons, from non-polar soft optical phonons at the edge of the Brillouin zone, currents associated with the transverse polar optical modes, plasmons, electron plasmons, can they be pairing the electrons? Non-cancelling contributions of the polar optical modes in between the upper and lower frequencies, phonon modes localized around the dopant impurity sites. These are kind of a local phonon picture by Gorkov. And then also there's been models involving the formation of polarons and bipolarons. Preformed pairs have also been discussed. And then the final one, of course, is what about the optical phonons? And this also has a long history, starting with Gurevich, Larkin, and especially Takada in the 1980s. So we thought we would do some new experiments to try and get a handle on what's going on. And we measured the pressure dependence of superconductivity in strontium titanate. So here's the resistivity versus temperature at different pressures. And you can see here the red curve shows that superconductivity is rapidly destroyed with very small pressures, just a few kilobar, 5 kilobars. So the electron bands and the electron density are not changing hardly at all over this range. So how could it be that superconductivity is destroyed so quickly with pressure? And this is just to remind you that there's also a dome of superconductivity as a function of carrier density. So to go back and think about this problem, we considered how do the electrons interact with the polar optical phonons and the electron degrees of freedom in the lattice. So here is the interaction function between two electrons added to strontium titanate, and it depends here on the dielectric function, the wave vector and frequency dependent dielectric function. And the dielectric function is given by contributions from two terms, the ions, the polar phonons, and the electrons, which are plasma modes. So omega p here is the plasma frequency, and this is the dispersion of the low frequency plasmons given here has a linear dispersion where Vf is the Fermi velocity. And then capital omega p is the longitudinal optic phonon frequency. And omega of q here is the transverse optic phonon frequency, which disperses like this. So close to the ferroelectric quantum phase transition, the gap here in this spectrum goes to 0, and that's where you would have a ferroelectric quantum critical point. And all these parameters are known from independent experiments, so that everything here is well defined. So we can rewrite the dielectric function, and in fact the interaction. If we put the dielectric function into the interaction and rewrite it in this form, we can identify new modes, normal modes of this coupled electron-phonon system. And these new modes we call omega minus and omega plus. And with those are what we call hybrid longitudinal polar modes. And they're shown here for a metallic density of 10 to the 18 carriers per cc. And you can actually measure these resonances in Raman scattering in underdoped samples. So instead of now having a system of polar phonons and electron plasmons, because the two are strongly coupled, the correct degrees of freedom that you actually measure in experiments look like this, and they're actually hybrid polar modes. And we think that these are the modes which are the predominant pairing mechanism for the electrons in strontium titanate. If we go to the low doping limit of this interaction, so towards the insulating state, then these omega minus and omega plus become the transverse optical and longitudinal optical phonons. And if you go up to high doping, then they become the plasmons of the metal. So what you can notice here is that when we tune the system to a ferroelectric quantum critical point, you're actually tuning this interception point here all the way to 0. It's easier to see in the low doping side. So when you tune the transverse optic mode frequency to 0, then you open up this large negative region of attraction for electrons down here. But the same here. These attractive parts of the function become much bigger as you go close to the ferroelectric quantum phase transition. So to see what happens for TC, here we have just a weak coupling gap function, which can be solved self-consistently. On both sides, Tc is the superconducting transition temperature. And then for U, which is the interaction kernel, we use the Kmk kernel, which is referred to in this paper, which is an approximation of the full Ali-Ashberg equations for superconductivity. So if we go through this model, we get a picture that looks like this, where the Tc versus carrier density has a nice dome structure, which is recreated here. And also, we have the fact that Tc is strongly suppressed as you increase the pressure. So that seems to be fitting quite well with measurements. And again, in here, there's no adjustable parameters. There's just the 0 temperature parameters for strontium titanate, which are measured from independent experiments. And for a reasonable choice of model parameters, we get that Tc comes out to be around half a Kelvin. So putting that together, we have a picture like this, where ferroelectric state here is suppressed to 0 to a quantum critical point. And then as you add in electrons into the lattice, there's a superconducting dome here, which forms quite close to the ferroelectric quantum phase transition. In this case, it's niobium-doped strontium titanate. So this is reminiscent of what's seen in many metallic magnets, where superconductivity forms around a magnetic quantum phase transition. And the prediction of the model is that for optimal doping, we recover the same kind of effect, where Tc is maximized close to ferroelectricity. But there's a prediction of the model in the very underdoped side that this will actually go to 0 close to the ferroelectric quantum critical point. So for very underdoped samples, there's a prediction to be tested there. So just making it look a bit more three-dimensional, it looks like this. So ferroelectrics are insulators, but when you put in electrons, they can still maintain a polarization, and you can actually tune the ferroelectric transition to 0 with carrier density. So there's a third axis here. And when you do that, you have a dome of superconductivity within this model forming close to this point. And we see this as a route for searching for new superconductors mediated by these hybrid polar modes. And I should point out that the model also works in potassium tantalate, which is also a quantum ferroelectric, which you can gate carriers using the ionic liquid method, and you also see a dome of superconductivity in this case. So just to recap, so superconductivity seems to be mediated by hybrid polar modes, which are the coupled degrees of freedom of the electrons and the ions, and maximized close to the ferroelectric quantum phase transition. Why is the attractive interaction so strong? It's because the bosons are polar. They're charged objects which are not screened out by the conduction electrons. So the electrons feel an interaction on the scale of the Coulomb energy. And why is TC so low? Well, that's because the density of states is so low. And if you increase the carrier concentration, then the electrons screen out the interaction and make it weaker. But TC may be boosted, we think, in materials tuned to the board of a finite wave vector polar phonon instability, such as antiferroelectrics or quadrupolar, higher types of states, or by combining this interaction with a magnetic pairing interaction. So prospects and applications for quantum criticality in dielectric materials, well, there's an many materials to study in this case. No one has yet looked at antiferroelectric materials, and there's many other ferroelectrics to look at, and many of these are suitable for doping electrons into the lattice. There's an opportunity to search for topological states, such as vortices and skyrmions in paraelectrics tuned close to quantum criticality. For applications, these materials also have a strong electrocaloric effect, where you can apply electric fields at low temperature and get large refrigeration capability. And then there's an opportunity to search for more superconductors of this kind. And on the electrocaloric front, we're now developing ferroelectric and magnetic refrigerators using quantum critical materials, which have a large magnetocaloric or electrocaloric effect. So these systems can go from around 5 millikelvin to room temperature with smooth suites, completely free of liquid helium, no helium-4, no helium-3. And it's very easy to have many tuning parameters here: pressure, strain, field angle, and so on. So these ferroelectric materials at low temperature have an electrocaloric effect like this, where you can apply an electric field to a disordered material. You do that isothermally, and the dipoles line up. And then you isolate your experimental system and the refrigerant from the rest of the world, and you sweep down the electric field adiabatically, and then you have to go back to this curve, and the only way to do that is to lower the temperature. And so we're now making these into millikelvin solid-state refrigerants. So just to acknowledge my collaborators in Cambridge: Gill, Lonsrich, Montu Saxena, and James Scott. Jason Lashley for thermal expansion measurements in Los Alamos, and Carsten, Jamie, and Elisa Sajtovic in CBPF in Rio. So thank you for your attention.
Okay, have time for questions.
I was curious, in many heavy fermions, you see the quantum critical behavior of the metallic normal phase, which has this linear resistivity, etc. And how about here? Is there a normal phase signatures which are exotic?
Well, there's the normal. Is this actually what? There's the normal.
Do you prefer to use this?
Hello? Oh yeah, that's better. Yeah, so there's the normal phase here of the quantum paraelectric, which would be the analog in the insulating state. So instead of, say, a T-linear resistivity or a logarithmic heat capacity, here we have a quadratic electrical susceptibility. Yeah. So, but what I'm saying is that this phase is a very interesting phase itself. And then if you dope it, there is something very interesting in strontium titanate. It has a quadratic resistivity up to over a very wide range of temperatures. But this is not a Fermi liquid quadratic, because the Fermi energy can be less than 1 Kelvin. So you're measuring quadratic resistivity in an area where you don't really have a Fermi surface. And the normal state behavior is currently not explained.
I have perhaps a different question. We saw strontium titanate earlier this morning underneath iron selenite. Do you think the mechanisms you have here in bulk strontium titanate may play a role at that interface?
I think it hasn't been checked out in detail, but yes, it's certainly a possibility. And that's one of my extra slides, is to say that wow, look, you go from 1 Kelvin up to 100 Kelvin. And what's the reason for this? Maybe it's possible that you could here be actually combining the polar phonon, the hybrid polar mode mechanism with the magnetic pairing mechanism. So maybe you have 2 bosons helping to support superconductivity in this case. But you also have the finite wave vector instabilities like BKBO, where these have polar modes at a finite wave vector. And Kotliar from dynamical mean field theory has identified that it's these kind of breathing modes and the longitudinal optical modes which are the main things coupling to the electrons. So in a more phenomenological model of this, maybe it looks something similar to what I presented.
There is a superconducting phase only on one side of the phase one, this one.
Mm-hmm.
But if it's these polaron modes that are actually created near the quantum critical point on both sides, shouldn't you have?
Yes, so since this work was done, both sides of the phase diagram have actually been explored. I don't know whether I have anything here on that. Yes. Yeah, so here's a case where you can tune through the quantum critical point into the ferroelectric phase by calcium substitution. And this curve here shows the ferroelectric phase transition temperature being suppressed to 0 with carrier concentration. And in these cases, the superconductivity appears right the way through, and it's not really been tested out properly, but it seems to show that there's a peak around the ferroelectric phase transition. And also, that's also been done with oxygen-18 isotope tuning as well.
I actually don't have a scientific question. I just have a quick comment about the single layer iron selenide on top of STO.
Uh-huh.
Yeah. I just want to quickly mention that this is actually done in our institute. Mm-hmm. So if you visit, you can actually talk to this group and find out all the nitty-gritty.
I'd very much like to. Thank you.
Yeah, please.
Okay. If no further questions, let's thank our speaker again.